Hi everyone, today's tutorial will be about number representation. I'll be showing you how we convert denary to binary and vice versa. Now it's important we understand when we do the conversion, we need to list the following numbers, which I'm going to explain to you in a bit why we need to do that. So we first have to do basically 1 multiply by 2, we go 2 by 2, we have 4, 4 by 2, we have 8, 8 by 2, 16, 16 by 2, 32, 32 by 2, 64, and so on. Which in a minute I'll explain to you why we do that. Now, binary, first we need to go back and understand what is binary. Binary is a base 2, 2, which is the 0 and 1 number system that is made up of only 2 numbers. While decimal or denary, it's base 10 because we have 10 fingers. So it's 1, 2, 3, 4, 5, 6, 7, and so on. So this number system is the base for all binary code, which is used to write data such as the computer processor instruction used every day. So a short for binary digit. Yeah, so the B, it comes from binary, and the digit, that's why we put them together and we call it a bit. It's the smallest unit of data on a computer. Each bit has a single value of either 1 or 0. It's ready to run programs are often identified as binary files and given a file name extension .bin. So that's why we call executable files binaries. So data is represented in digital format based on binary base 2 principle. So the smallest element of data is the bit or the binary digit, as I mentioned, B and the it from digit, put them together and we have bit. This can be represented by a 0 or 1 or and 1. So when bits are grouped together, they can be more useful unit of data. For example, 8 bits form a byte. So if we look at this ASCII table here, we have the decimal, binary, octal, hexadecimal. The computer memory is made up of millions of bytes. Different computers have different sizes of memory, and the size of computer memory is stated by the manufacturer. That's why when you go and buy a computer, when you ask about the memory size, normally they will tell you it's either 18 gigabyte, 16 gigabyte. Sorry, not 18 gigabyte, yeah, 16 gigabyte, because that's 8 multiplied by 2, 16, 64 gigabyte, 128 gigabyte, or megabyte, whatever. It's all back again to the 1, 2, 4, 8 rule. So here we can see the decimal. If we want to convert it to binary, as you can see, 1 is 1, 2 is 1, 0, 3 is 1, 1, 4 is 1, 0, 0, 5, 1, 0, 1, 6 is 1, 1, 0. And how can we know, for example, this is not 110, this is 1, 1, 0. That's why we call base 2, or we use the letter B. Or if we want to know whether this means 1, 1, 0, then it's base 2 binary, and if it's 110, then we put the letter D, denary or decimal, next to it to say basically this means 110, or sometimes we put a small 10 underneath it when we say base 10. Okay, so to convert denary to binary, you must firstly know the base 2 rules. Okay, this is 1 multiplied by 2, 2, 2 by 2, 4, 4 by 2, 8, 16, 32, 32 by 2, 64, 64 by 2, and 2, 8, and so on. So as you can see, programmers can choose a storage type with minimum waste while a good fast execution. That's why we follow this process. So converting denary to binary. So let's look at this example. So 00101110 is 46. Okay, so how do I know this is 46? So 46 in binary, it's 101110. As you can see, any zeros on the left, we kind of discard them. We don't really deal with them unless it's specified in terms of number of bits. But at this moment, 46 is 1, 0, 1, 1, 1, 0. Let's find out how we reached to the conclusion. So the first thing you list basically your numbers here, the base 2. 1 multiplied by 2, 2, 2 by 2, 4, 4 by 2, 8, 8 by 2, 16, and so on. Now, you don't have to put the whole list. I mean, you stop where you think that last one basically is the end. So here, as you can see, I assign the 0 next to the 1 below the 2, the other one, the third one here, the third bit, we put it under the 4, and so on. And then if we add these numbers, 32 plus 8 plus 4 plus 2, we get 46. Why we add those only? Because they have the number 1 underneath them. So the ones with 0, we don't add them. So we work this out by looking at the headings and adding the numbers up. So if we put 32 plus 8 plus 4 plus 2, we have 46. Therefore, 46 is represented as 101110. Then we don't need to worry about anything after that because it's going to be zeros anyway. Because 46 here, it's more than 32 and less than 64. So I can't put 1 here because 46 is less than 64, but it's more than 32. So I will go after the 32. So that is the first one, 32. Then what I do, if it's in my head, I would say, okay, 46 minus 32. Then what do I have left? Then I have left 12, 13, 14. Yeah. And then now the 14. The 14 is less than the 16, but it's more than the 8. So straight away, I put a 1 under the 8. Okay, so now 14 minus 8. So what I've got left is 6. Now 6 is less than 8, but it's more than 4. But I know 6 is basically 4 and 2. Of course, it's not 4 and 1 because that will make it 5. So it's 4 and 2. And that's how we have 46. Let's look at another example, 61. Now 61, it's less than 64, but more than 32. Okay, so straight away, I know I will stop around here. Okay, because it's not passing the 64. So I put 1 underneath the 32. So now I've got 32. So 61 minus 32. Then what's left? So first I have to make sure I've got my maths right because you can easily make mistake with this. So 61 minus 32, I've got 29 left. Okay, now 29, it's less than 32 and more than 16. So I put 1 under 16. So 29 minus 16, I have 13 left. I know 13 is more than 8, but less than 16. So 13 minus 8, I've got 5. That's quite easy now because I know 5 will be 4 and 1. 4 and 1. And then I just put 0 under the ones I don't really need. And that's how I get 1, 1, 1, 1, 0, 1. Any zeros on the left side, I don't really care because that's something is not won't be added to it. So if you want to practice yourself, just you can do that. It's quite easy. So like I said, so let's take an example here, 19. So 19, I want to convert it to binary. So let me just look here. So I have the number 19 and I want to convert it to binary. So I know this is base 10 because like I mentioned to you, that's 10 underneath it, then we know that. But if I have, for example, I have 101 and I want to know this is 101 or 101, then normally we put 2 underneath it, which means base 2. Okay, so now, so straight away I add 1, 2, 2 by 2, 4, 4 by 2, 8, 8 by 2, 16, 16 by 2, 32. So I don't need to go to 32 because it's 19 less than 32. So I put here 1, so 16, so 17, 18, 19. So I've got 3 left from that when I minus the 16 from the 19. So I got 3 left. So I know it's the 2 and the 1 because 16 plus 2, 18 plus 1, 19. So that is 0 and 0. So 19 in binary will be 1, 0, 0, 1, 1. And that is base 2. Okay, it's quite simple. And in terms of the process, I want to find out. So for example, let's delete the 19 and I want to know whether my, if I want to convert it the other way around. So I want to know this one, what is it in denary, basically. So let's say I've got something like 10011, the same process, exactly the same process. I take the 1 here, I take the second bit there, and then I put 0 here, and then I put 0 here, and then I put 1, and then when I add them up, will give me the same process. Now, let's pick another example, and I want to convert this one, which is 10101. So this is base 2. So what is it in denary? So let's have a look. So I take the first bit, put it here, 1, second one is 0, and then the third one here, and then 0, and then 1. So let's add them up. See, as you can see, this example I just came up with it. So 16 plus 4, 20, 20 plus 1, 21. And that is base 10. Yeah, let's double check. So 1, 0, 1, 0, 1. So 16 plus 4, that's 20, plus 1, 21. And you can have a look yourselves. There are so many websites online where you basically you could do the conversion and you can see I got the number right, which is 21 in denary. As you can see, this is quite easy way. If you follow the 1, 2, 4, 8 rules, without it, you basically won't be able to do it. There's other methods where you can do it, but this is kind of an easy way. All you get to do, because it's base 2 rules, you 1 multiply by 2, get 2, 2 by 2, 4, 4 by 2, and so on. Also, let me just quickly talk about the most significant and the least significant. With the most significant and least significant, when it comes to binary, that's something we need to know. If the left, the furthest number on the left side, so let's say here we have 1, 2, 3, 4, 5, 6 bits here, yeah? But again, I mean, I could put 0, 0, 2 and then make it 8 bits, just like this example. Normally, we always look at the furthest binary to the left, and that will be the most significant. And the furthest binary to the right, we normally call it the least significant. So if I have so let's say here, we have 8 bits, 8 bits binary. So because it's 8, because here 1, 2, 3, 4, 5, 6, 7, 8. So this number here is the furthest, will be the most significant. And while this one here will be the least significant. Yeah, so for example, let's look at another example in terms of the furthest. So let's have a look at this one here, 2110 here we're looking. So I'm looking here at this here. So that will be my most significant, and then here will be my least significant. Next tutorial, we're going to look more into addition and subtraction, and also we'll be looking at signed and unsigned binary, and then you'll get the idea